Okay, so this video is going to cover this file compression quiz number 2. And this is kind of a really good teaching moment how to do some of these things. So this is why I like using quizzes. But so let's go through this. So this run length encoding, this was in one of the readings I had you do. I think it was in both in the file compression lesson number 1 and number 2, but let's go through it. It says run length encoding, RLE, is a data compression technique that replaces runs, sequences of bits with the same value, with a number representing the length of the run. RLE can be used to compress color images, especially when the colors are from a limited palette. The following is a run length encoding of an 8x8 icon with 3 colors: R signifying red, red run, G signifying a green run, and Y signifying a yellow run. So you got 3 Y, so that means there's going to be 3 yellow cells, 2 reds, and 3 yellow. And so anyway, when you do this, what I would do is I would draw out a 8x8 grid, and I would put Y, 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 R, R, Y, 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 and then on the next row I would do Y, Y, R, G, G, R, Y, Y. And so I did this down here, and I end up getting this. Now, you're going to be on your AP test, and you're not going to be able to draw in the colors, but at least you could look at this and go, well, what shape is it creating? Okay, well, looks like it's creating like a red, a green diamond, and kind of a red diamond as well. But what are the answers that you could choose from? A green diamond. Okay, a green pentagon, a green triangle, a green circle, a green square. So a green diamond is what it's creating, and I kind of did that down here. It's none of the other ones. It didn't have anything to say about red or yellow, so you ignore that in the test question, and then you have that. So let's see here. Number 2, byte pair encoding is a compression algorithm that replaces the repeated pairs of characters in a string with a character that isn't in the data and creates a table of replacement mappings. Here's the output from a byte pair encoding. So your message could be encoded like this to compress it to save space. Now, you need the actual key in order to turn this back into your original message. So you're using the key here to turn back the original message. So I see the letter Z and replace Z with TH. So your message would start, it would be THE, because there's the E there, and Z would be TH. Then you've got M, X, X is OR. So I've got M, OR, and then E. And then I've got THAT, Y is, I got Y, and then B, so OU. The more U, R, and then F is EA, so R, EA, and then D, so the more you read. Okay, and so you get the point here. Here's what the actual message is. The more you read, the more things you will learn. The more that you learn, the more places you'll go. Okay, so all I'm doing here is just using my key to fill it in with the original, okay? And then it spells out that sentence that I typed in. So, I'm actually going to get rid of that. And I'm going to save it real quick so I don't lose, and then I won't save it again. Okay, which algorithm, compression algorithms vary in how much they can reduce the size of an image. Which of the following would likely be the easiest to compress? Okay, again, so this question is testing whether you understand that images with more pictures and more detail, especially with color, those are harder to compress. Pictures with less color are easier to compress. So the easiest picture in here is just the black and white unicorn. Those are only two colors, black and white. This one would be the second easiest because there's only, there's white, there's a little bit of a dark pink and a light pink and some blue and yellow and red and orange and green and light blue. But those are all the colors in here. When you start getting into things like these colors, B and D, I'm not really sure which one would be easier to compress. I suspect it would be B because the colors are more alike. This one has got more the different shades of green, the pinks, the darker pinks. So I think D would be the hardest. The unicorn would be the third or the second hardest, and that would be the third hardest, and that'd be the easiest. So your answer for 3 is C. And I am going to go into, I've got this RGB color, but you can kind of see all the different shades of red here. And I'm going to go through and explain the RGB color wheel for you guys here in a minute. But you can see there's a ton of different shading. And so the more of the different shades that you have, the harder it's going to be for your compressor technology to compress the file. All right, 4, consider these 2 files. You got a 1-minute video of a cat pouncing furiously on a twisty tie, and 2, a download of The Lion King that is an hour and a half long. So anytime you see these, is it possible for The Lion King to have a smaller file size than the shorter cat? Yeah, but you're gonna, you're probably going to lose a lot of your data, and your picture is going to have real bad quality with the Lion King video. So it's possible, but it's going to be bad. So what are the answers? Yes, as long as the Lion King video is compressed with an open, non-patent, okay, I don't know what non-patented standard is. B, if the Lion King video is compressed with lossy compression, so yeah, that's true. If you use a lossy compression and you lose data and quality, you could make Lion King smaller than the cat. C, yes, but only if the Lion King video is produced by a major company. No, that's not. D, the Lion King video will always, and so no, that's not true. It will always make up more as long as it's high quality, but if it's really bad, you can compress it. 5, Cora is planning to take photos of her cat and print posters of each photo to hang on her wall. What advice will help her the most in creating, now this is the key, high quality posters? Okay, she wants high quality. So A, she should save photos with the lossless compression algorithm to ensure that the posters are of the highest quality. That sounds pretty good to me, because we want the highest quality. Lossless, you're not going to lose any of the information. B, she should have the photos on JPEG photos, because only JPEG photos can be printed out. That's not true. You can print out different types of images. There's GIF images, there's PNG images that you could, print out. So B's not right. C, she should save the photos as black and white, as color photos can't be saved in full detail. It's also false. Photos can be saved in full detail. And black and white probably wouldn't give the kind of high quality that the question is asking for right there. D, she should take the photos using a real camera, as phone cameras can't save high resolution. That's also not true. Phone cameras can save high resolution photos. So your answer is clearly A. 6, let's see here. Digital images can be represented and stored by the red, green, and blue values RGB of each individual pixel in the image. If you are manipulating a digital image and overwriting the original image, so if you are manipulating a digital image and overwriting the original image, which of the following describes a lossless? Okay, so this is where you don't lose information, all right? So swapping the values between R and G to turn the green parts of the image red and the red parts green. So when you swap one for another, have you lost any data? No, you could unswap them back if you want. So that's lossless. That's a lossless technique that is done, okay? So A is your answer. Let's go through the other ones. Set the blue value of each pixel to 0 so it makes the blue parts of the image go away. If you set, again, look at this. Let's look at blue. Aren't there like a million different blue values in here? If you set one to 0, do you know what the original one was? And so that is an example of lossy. You would actually lose your data. So that's not lossless. Let's come back to C because that's harder to explain. D, create a grayscale image by averaging the RGB for, okay, so when you average, anytime you see average, you know that that is lossy and not lossless. Why? Well, let's just run some average calculations. Let's say your average is 7.5, 7.5 divided by 3, that is 2.5. How about, let's do this down here. 7.5 divided by 2.5, the average is 2.5. 2.5 divided by 1 equals 2.5. Okay. 5 divided by 2.5. Sorry, I wanted to do 5 divided by 2 equals 2.5. So anytime you're given an average, you don't know what the original number is because I just showed you 3 different calculations where the average comes out to be 2.5. So when it talks about averaging RGB colors, you know that that's going to be a lossy type compression because you don't know the original values, okay? C, compressing the image by decreasing the number of bits per RGB value by 1. This one seems like just from the wording that it would be correct because you're going, well, I'm just removing 1 bit, and couldn't I just add that 1 bit on? All right, so the answer is no, and let's talk about why and what these color wheels are doing, okay? So let me increase this a bit. Maybe I can't. All right, so you've got RGB, okay? Red, green, blue. So all values are of this are the highest one here. Let's see where I got 255. That's my highest value for red. It's my lowest value for red. If I go to the corner, my lowest value for red is 0. So, how did we get 0 as my lowest and 255 as my highest for red? The same with green and same with blue, okay? And I kind of wrote this down here. So all your colors are 8 bits, R, G, and B. They're 3 different 8-bit color codes, okay? So 8 bits is 1, 2, 4, 8, 16, 32, 64, 128, which comes out 0 to 255. So there's 256 different shades of red in your RGB color wheel, okay? Same with blue and same with green. So what we have here, if we were to take 256 times 256 times 256, we get 16.7 million possible color combinations here. So 16.7 million different combinations, all right? And so, again, these values right here, F7, 51, 54, this is their decimal equivalent, okay? 127, 81, 84. But since hexadecimal only uses 2 characters in here, instead of potentially, 255 for each of these. This just makes it easier with hexadecimal using less characters, all right? So there's 16.7 million possible color combinations. So if you remove 1 bit from each RGB, you would have your, okay, so again, I remove the 128 bit. So I've got 1, 2, 4, 8, 16, 32, 64. If you added all those together, you would have 0 to 127, which is 128. 128 times 128 times 128, you only have 2,970 or 2,097,152 different color combinations. So if you just remove that bit, you do remove it, but you don't know the original bit what it was equal to. And so that's a lossy type compression, okay? But this is going into the entire thing, why you can't just remove a bit. You actually could, but your colors wouldn't come out with as many different shades as this right here. Okay, this has 16.7 million possible colors. This only has like 2.1, close to 2.1 million. So removing one of those bits, you have a lower quality of colors and shading and everything. And since you removed it, you don't know what that bit was actually equal to. And so your answer for number 7 cannot be C. It must be A. Swapping is just trading back and forth. That information is still saved. Okay. Let's see here. 7. So I don't have an official database unit in this class, but I do go through databases and how you should think about databases. So let's talk about this. An auto parts store keeps the following database of information about their inventory of thousands of different auto parts. Some customers bring in the auto part, but the majority of customers come in providing information about their needs. So my tire pops. I go into the store and I say, hey, I need a new tire. I don't go in and say, I need the tire and here's the part number and who's it's made by. That's typically not how it would work. You don't usually ever have a part number. And so what you would want to do, here's your information, your car, the auto part name, shelf location, part number, tool, price, number in stock. Okay, so this company has 19 different alternators made by Bosch for Chevrolet cars, and it's located on this shelf, and here's the part number and price. So the database categories need some type of organization and sorting for efficient access. Which of the following will give a fast response to availability of the need? Okay, so I'm going to go through a couple that should be wrong at first, and we'll talk about why. So again, B, sort first the part number and then according to price. Well, the only way this would be a good way to do it is if the customer came in with the part number. And again, most customers, they come in and they're like, I need an alternator. They don't come in and say, I need part number 123 ZXY FFF or whatever. They would never remember the part number. All they would remember is what the part name is. So B is wrong. You would never want to sort the information like that, okay? D, sort first according to the auto part company and then according to part number. Think about how weird that would be. Hey, I need a Bosch. A Bosch what? Well, I got a Bosch and then the part number and I remember the part. Again, that wouldn't work. You wouldn't do it by the auto part number. So B and D are clearly wrong. This is kind of hard for high school kids because maybe you have never even been into an auto part or store before to change out, a part in your car. So you really kind of got to think through how the real world would work, which a lot of you haven't experienced yet. So this is going to be kind of difficult. So let's look at A and C. Well, A and C would both actually work, but one is more efficient than the other, okay? So let's say I went in for C and said, hey, I got a Chevy. I have a Chevy. So what would happen is all of the different Chevy parts would pop up, and then it would go down to the part number, okay? Yeah. Well, and this would again, the user wouldn't know the part number. They would say I have a Chevy though. But think about the hundreds of different parts for a Chevy. There would be tons because not only is Chevy like think about all the different Chevy cars, Chevy Camaro, Chevy I think a Suburban is a Chevy or no, it's a GMC. I don't know the different Chevy cars, but whatever. There's a lot of them. So just telling them the car name doesn't really narrow it down very much. If you go in and say, hey, I need an alternator, okay, you got your alternator. So it would pop up all the different alternators for all the different types of cars. But then if you narrow it down again to Chevy, the car name, then it's going, okay, I've narrowed it down to alternator and then the name. And then there would actually be a bunch of different companies that make alternator, Bosch and whatever different companies that make them. But at least you've narrowed it down to the name and the car. Then we can narrow it down to the different makers and how much the price is. Again, your customer's never going to care about the part number. So anyway, hopefully this makes sense. A is the correct answer. 8. Again, we're trying to display the numbers in ascending order, so that's low to high. So there's a couple ways you could do this, but probably the fastest. So let's see here. I've got, for this first one, I've got 1, 2, 4, 8, 16. So let's see what that is. That's we got a 0 there, 0 there, 1 there, whoops, 1 there, 0 there, and 1. So I've got 16 plus 4, that is 20. Okay, 20 is less than 123, so 123 would be, if we just had this so far, we've got 20, 123, and we need a test for D7. Well, how is D7 figured out? So if you recall, you've got 16, I'm sorry. Yeah, 16 to the, where is this at? To the 0 power. And if I multiply this by 7, and then I add in, sorry, it's kind of backwards, but 16 to the 1st power plus, let's see here, D, what's D equal to? Well, we've got 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. A, B, C, D, E, and F. So, in its decimal version, you got 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So, this might make it easier for you guys to see. Okay, so D is equal to 13, so I put 13 there. And so my answer to this would be 16 to the 1st, or 16 to the 0 power is 1. 1 times 7 is 7. So I got 7 plus, and then 16 to the 1st power is 16. And this isn't plus, it's multiplied. So 16 times 13. So 16 times 13 is 208. 208 plus 7 equals 215. So 215 is greater than 123, which is greater than 20. So your answer is what? This one, then this one, and then this one. So your answer for 8 is B. 9, if the decimal number 89 is represented by ASCII character Y, what binary number is used to store? Okay, so the way I'd figure this out is A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y. So in the problem it says 89 is represented by Y. You got 88, 87, here, 86, 85, 84, 80, 83, 82. Where are we at here? Let's see if we can do this. Q, R, S, T, U, V, W, X. I'm one off, so I need to do one more number. 81, Y. Okay, Y is represented by 89. So what's represented by Q? Q is represented by 81. So 81. So then all I do is just, what I've been doing. So 64, 32, 16, 8, 4, 2, 1. And then I'm going to go to the next page. I'll just do it right here. So I got 81. So to add those up, I got 1. 64 plus 32 is greater than 81. So we get rid of that. 16 plus 64 is 70, 80. So that's on. And then that'd be 88, that'd be 84, that'd be 82, that'd be 81. So 81 is its binary equivalent right there. So you've got 1010001. So your answer for this is B. For number 9, the answer is B. So you'll definitely want to study these and know how to do these both on this compression quiz number 2 and the compression quiz number 1 so that you guys can do well on your graded quiz. And this video is done.